Okay, so we're ready for our afternoon speaker here, Dr. Laura Christianson, Assistant Professor of Water Quality in the Department of Crop Sciences here at the University of Illinois. Founded and co-leads the Illinois Drainage Research and Outreach Program, IDROP. She formerly worked as a research engineer on the design of woodchip bioreactors for removal of nitrates from point and non-point sources, studied options to improve ditch drainage water quality in the Mid-Atlantic. Let's give her a warm welcome, Dr. Christianson.
Okay, so you will have noticed that I shortened the title, but that's all you need to know. So we're going to go bioreactors. Woo! That's how you pronounce that. We are going to talk about three things, three buckets. I'm most excited about the third one, so we're going to go fast through the first two, starting with how well do bioreactors work in Illinois. And as I was sitting at the table this morning, I realized I'm not going to explain what a bioreactor is or how bioreactors work. So if you don't know what a bioreactor is, you might be at the wrong meeting, or you can ask Jeff Kerwin, who's sitting here at the front. He can tell you. Okay, so how well are bioreactors working here in Illinois? Over the last 6 years or so, my group has monitored 15 plus or so bioreactors across the state of Illinois, and about 7 of those bioreactors we consider to be conventionally designed bioreactors designed to the NRCS conservation practice standard. So of those 7, combining all those 7 together, we have 22 site years of conventionally designed bioreactors. You see at the very bottom there, 22 site years. And what we're seeing from these 7 bioreactors is that we're removing just under 20%, we're providing just under 20% in loss reduction. So for me, this is not very good. I think bioreactors should be operating better than this. They are designed to do one thing, so I'm not super excited about a 20%, less than 20% in loss reduction. But let's talk about these numbers a little bit more. What does this mean in terms of in loss actually coming from our fields and in loss that we're removing? These 22 site years, mean median, we're losing between 25 and 30, again, mean median, pounds of in lost per acre. From these 7 bioreactors, again, 22 site years. These include farms that are doing cover crops, farms that are not doing cover crops. One farm is an organic transition farm, so you see a range there for that dark blue bar. But from that, coming from the field, we're removing about 5 pounds, on average 5 pounds of in per acre, our bioreactors. Now, if you take the acres out of it, we're removing, across these 22 site years, roughly mean 150 pounds of in removed per bioreactor per year. Okay, so some of you will remember that bioreactors in our nutrient loss reduction strategy in Illinois, bioreactors are rated at 25%. And again, I'll just mention, we were achieving just under the 20% in that first orange bar. Again, I'm not super happy about 20%, but I do want to mention the NRCS does design bioreactors for a 20% in-loss reduction. That's in the conservation practice standard. That's how they design bioreactors based on the current revision to the standard. And so NRCS is doing their job. We're just under that 20%, but you do see we are slightly under the NLRS value. So how can we make bioreactors work better? This is where it starts to get a little more interesting for me because, again, not happy with the 20%. What do you all notice about these pictures? Pretty similar. These were all bioreactors designed to the same conservation practice standard. Again, standard. It's a standardized design. These are all long, skinny trenches filled with wood chips. That's part of the standard. And so in our research, we wanted to mix this up. If you keep doing the same thing that you've always done, you're going to keep getting what you've always have gotten. And so we wanted to try some different things, which is where our NREC funding came in. I'm going to talk about 3 different sites or 3 different farms here. And we're going to go quickly because each one of these could be its own presentation. We'll start with the top one, our baffling or baffled bioreactor. Our baffling bioreactor is at the University of ACE's Dudley Smith Farm. This bioreactor is 55 feet long, so it's about the same length as most of our bioreactors, our conventional bioreactors in Illinois, but it's 35 feet wide. So it's 2 to 3 times wider than most of our bioreactors, our conventional bioreactors in Illinois. We also added baffles to route the water more effectively since we made it so wide. How did this look? Pretty baffling, a big bioreactor with baffles. What did we learn here? We have very consistent performance at our Dudley Smith bioreactor, but again, it's just a big bioreactor. So performance is consistent. We're also removing phosphorus, which is something we want to dig into a little bit, but I'm not going to talk about today. Lessons learned, the drainage at the Dudley Smith farm, it wasn't an area that was historically had a lot of tile drainage, and so it just ends up being flashy, which of course impacts how our conservation practices perform. Our next bioreactor, next weird bioreactor is at the Crop Sciences Department Research and Education Center near beautiful Monmouth, Illinois. The first thing you'll notice about this bioreactor is that it's not one bioreactor, but 2 bioreactors. And so the idea here is that we had the opportunity to treat a really big drainage area. Most of our bioreactors are on drainage areas that are 30, 40, 50 acres. And so this was a big drainage area for one bioreactor. And so the idea with the design here is that drainage comes from the left of the screen, and most of the drainage water goes into what we call the main bioreactor or the base flow bioreactor. Anytime drainage is flowing, this bioreactor is flowing. Now, when we have a lot of drainage water leaving the field, the second bioreactor comes online, just by the way that we have the control structure set. So during high flow events, like in the spring after a rainstorm, both bioreactors are operating in parallel. The other difference here with this bioreactor is that water does not flow down this long, skinny way. Water flows the way that the arrows show. And so not only is it 2 bioreactors, but we've flipped the orientation. So they're 60 feet wide or 40 feet wide and 20 feet long. Lessons learned here. Oh, here's a picture. Flow comes from the top of the top field through those bioreactors, and then the outlets to the bottom. Picture of installation. And if you're wondering, what are these students doing with a shop vac on top of a bioreactor? My student, Miss Naranga Wikram Marathni, will have a poster tonight. I encourage you to ask her, what are you doing with the shop vac? And actually, it did work, so hats off to them. Lessons learned from the paired bioreactor at the Monmouth Research Center. Huge success story. We treated almost all of the drainage water coming from that very large drainage area. And so this is an important proof of concept for scaling the idea of bioreactor technology to bigger and bigger drainage areas. We also learned, though, that there is a trade-off. Because the bioreactor was so short, it was really just 20 feet long, there is a minimum hydraulic retention time to get good nitrate treatment inside those bioreactors. So it was a trade-off. Overall performance was very average. Now the last weird bioreactor that I'll talk about is on a private farm here in Illinois. Similar to the Monmouth one, this is a paired bioreactor design. So we have an in-ditch bioreactor here, shown here. This is what we call our woodchip mattress or woodchip bag. We made it by hand. It's just literally a handmade bag made of wood chips in the bottom of the ditch. If you're standing at that orange star, that's what it looked like during construction. And then a few years later, standing on the other side of the bank, looking upstream, you see some riprap, which was a part of our design, and then a large control structure. I point out the large control structure because that's also part of the high flow bioreactor in this case, or the ditch diversion bioreactor. The idea was that low flow going down the drainage ditch would be treated by that wood chip mattress. And then when we had a lot of drainage water in the ditch, high flow events, a portion of the water would get routed to the side to this diversion bioreactor. Lessons learned here, we did meet our design objectives. My most important design objective was that I did not want to back ditch drainage up. Our ditch systems are important flow conveyance systems for our farms across the Midwest, and so I did not want to back drainage water up in the ditch, and we did not do that. And our wood chip mattress was also very easy to build. We built it ourselves, but it didn't treat very much water. If you don't back drainage water up in the field, you're not going to route it through your wood chips. And so this wasn't necessarily something I would do again, but I did want to mention especially the ditch diversion bioreactor, because this is now a part of a new NREC project where we've added pumps to pump water from the ditch into that bioreactor. And I wanted to mention this especially because this new NREC project, importantly, very importantly, provided matching funds for our National Conservation Innovation Grant, which is a $1 million grant from the NRCS being led out of Illinois. It's a multi-state grant, and we could not have applied for that grant if we hadn't had the matching funds from NREC. So that's a huge deal for us. And we're excited to see how the pumps work. And you can't fake those smiles in the pictures. Okay, so here's where it really gets good, what I really wanted to talk about today. What about the wood chips? As researchers, we're really good at, for example, getting one kind of wood chip and then studying every single thing there is to know about that one kind of wood chip. We like to go deep, we like to go in depth, but the problem with that in terms of the real world is that there's more than one kind of wood chip in the real world. So there's lots of wood chip suppliers across the Midwest. Even if we have a preferred wood chip supplier for our bioreactors like Xylem, the wood chips at the front of the pile could be very different from the wood chips at the back of the pile. And so in this study, we wanted to get all the kinds of wood chips that we could, which ended up being 21 kinds, and evaluate the physical and the hydraulic properties of that spectrum of wood chips widely available across the Midwest. And so this was partially NREC funded, partially funded by the NRCS. We evaluated a whole slate of physical and hydraulic properties, starting with size, which I'm not going to go into today, but was very important actually for the NRCS conservation practice standard. We studied porosity of the wood chips. So watch the wood chips in the little jar there. Drainable porosity is what I'm highlighting with the yellow. Drainable porosity is those big pore spaces between the wood chips themselves. Those big pore spaces are responsible for the bulk flow that moves through the bioreactors. And so drainable porosity is really important. Wood chips also have a total porosity because wood chips themselves are porous media. And so there's little tiny micropores on the wood chips themselves, but those don't contribute to a lot of the bulk flow if you're thinking about water going through a bioreactor. So I'm not going to talk about total porosity today. We're going to talk a lot about bulk density of wood chips. Bulk density is a very simple concept of mass, normalized by moisture content, but mass of the wood chips divided by volume of the wood chips. And so if you have the same mass of wood chips, but smush it into a smaller volume, your bulk density increases, right? That makes sense. And then one of the most important hydraulic properties of wood chips is saturated hydraulic conductivity. Saturated hydraulic conductivity is how fast you can push water through wood chips. The picture that I'm showing is how we measure saturated hydraulic conductivity in the lab, that big PVC, 8-inch PVC pipe. You fill that full of wood chips, you saturate those wood chips, and then you run water up through the wood chips, and you measure the head loss across the wood chips, and that's related to the saturated hydraulic conductivity. Again, just the speed at which you can push water through wood chips. What that looks like in the lab is a lot of PVC, a lot of tubing, a lot of buckets, and hats off to Mr. Gabe Johnson, who is a master's student who led this work. He's now a PhD student at Iowa State University. And just to prove my point, we got a lot of different kinds of wood chips for this study. So the whole reason why this matters is because these physical and hydraulic properties are used in design models. For example, you see from the conservation practice standard here, size is one of the most important physical properties that's actually listed in the conservation practice standard, but the two values that go into the design model used by the NRCS to determine how big our bioreactors are, those two parameters are drainable porosity and saturated hydraulic conductivity. So those are two really key ones that we wanted to look at in our lab. Okay, so what we found across these 6 wood chip types, by the way, 2 of which had been approved by the NRCS for use in bioreactors in Illinois, As bulk density increases, as we smush those wood chips tighter and tighter, as bulk density increases across the bottom axis, drainable porosity goes down very consistently across the wood chips that we tested. So again, not rocket science. As you smush wood chips tighter and tighter into a given volume, those big pores get smaller and smaller. The reason why that matters for water flow is because as you smush those pores smaller and smaller, they also become less connected. And so as wood chips get more and more compact, the saturated hydraulic conductivity also decreases. So we can get water through not as well. So same graph, I just stretched it out. But one thing that we realized was very glaring as we were compacting all these wood chips in our lab was that we don't actually know, there's been no study of what is wood chip bulk density actually in bioreactors in the field. And so we can compact wood chips in our lab until we're blue in the face, but we don't know what the real value is for wood chip bulk density in bioreactors in the real world. So we came up with an idea. We know that bulk density is very simple, like I said a minute ago. It's mass of wood chips, weight of wood chips, normalized by moisture content, divided by a volume. So again, if you have the same mass of wood chips smushed into a smaller area, your bulk density goes up because volume decreases. So that's simple algebra. And the other thing that I like about bulk density is that it's very simple, so there's very few places to make an error. For example, it's not some complicated model with 1,000 different parameters that you have to plug into a supercomputer. The supercomputer spits something out that nobody can understand. This is very easy to understand, and it's easy to think about mass over volume, increased mass, increased volume, what happens. It's a simple model. So we thought, I think we can evaluate what bulk density is in the field by doing a fun experiment. And so this is what we did. We had a bioreactor relatively close on campus that was built in September 2019. We decided to excavate those wood chips out last summer. As we excavated, we weighed every single wood chip that we pulled out of that excavation. How do I know this? Because I was on bucket duty. Just in case you think I only moved paper around on my desk, I was actually on scale duty that day. So we filled buckets, we weighed every single bucket that came out, and then we corrected those all for moisture content. Volume was a little bit trickier, so we estimated the volume of each layer that we excavated in 3 different ways, and I'm going to talk about those next. In increasing order of coolness, the first way that we estimated volume of each layer that we excavated was using laser level surveying. So we had a survey rod, and we just surveyed the excavation that we made. The next coolest way was that after we had excavated some of those wood chips out, we laid plastic and then pumped water in. We pumped water in through a flow meter. A flow meter tells you something like gallons, and what are gallons? A volume. So that's how that was our second method for getting volume. We filled up water to the very top and then also pumped the water out through that flow meter. Now the coolest way to do volume was using the LiDAR on our iPhone 12s. We did not charge our iPhone 12s to our NREC project, although maybe we could have. So just to go back to set a little bit of context for what are the kinds of numbers that we're looking for here, before we actually started crunching our numbers, the kind of rule of thumb number that I would have been looking for, what's a normal wood chip bulk density, was around 200. So keep that number 200 in your head. A lot of previous lab studies that have packed new wood chips into columns, they pack them at about 200. So in my head, that's the number that I was looking for. What did we actually find? On the top layer at the Ag Engineering Farm pilot bioreactors, our average bulk density was over 250. So it was much higher than what I was thinking. And I was also thinking this is the top of the bioreactor. So that should be the lowest bulk density, because it's not at the bottom, it's at the top. But the real shocker was that as we went deeper and deeper into the bioreactor, those bulk densities decreased. They didn't increase, they decreased. So we thought, let's double check the numbers. There's not very many places to go wrong with this method. It's mass over volume. And so let's dig into this more, because this is kind of interesting that the bottom of the bioreactor was the least dense. Oh, I also want to highlight these numbers around 150 or so. We couldn't even pack wood chips in our columns that low at that low of a density. So it was really a conundrum for us. So we wanted to dig into this a little bit more. And we had the opportunity to, last summer, after trying our proof of concept method of surveying and water pumping and LIDAR, we had some new bioreactors and some old bioreactors that we could test this bulk density idea at. The new bioreactors were parts of partnerships and other projects that we were doing, but we realized we have weigh tickets from the wood chip dump trucks, and those give you a mass of wood chips, because those big wood chip dump trucks, they weigh themselves to know how much to charge you. So we got the weigh tickets, and then as the big bioreactor pits were excavated, we surveyed and we also did LIDAR on those. And then we had the opportunity at 3 old bioreactors that were recharged last summer to trial our LIDAR method at the bottom of those bioreactors as those wood chips were excavated out. So what did we find? The new bioreactors were very confident, feeling good about our method, and those new bioreactors came up at bulk densities around 200. So that was my kind of rule of thumb value. That sniff test makes me feel good that our method is right, 200 plus or minus 20. But again, the old bioreactors at those bottom wood chips came up at very, very low bulk densities. Again, we can't even pack wood chips in our lab at this low of a bulk density. And so we're very excited about this research right now. It was something very fun for us to dive into. Our working hypothesis has to do with the fact that those bottom wood chips are really wet. They're very wet. And so in our bulk density process, we account for wetness by correcting for moisture content in the top. We use dry mass, but of course water takes space too. And so we're working through these data right now. In fact, when we test it in the lab, our wettest wood chips, you see there in the circle, our wettest wood chips do have the lowest bulk density. So I think it has to do with the fact that water also takes volume, even though we account for water in this equation. Okay, so why does this even matter? I just want to come back and remind you that physical and hydraulic properties of wood chips are all interrelated. And these physical and hydraulic properties impact how well bioreactors work. They also impact how well we can design bioreactors. And so we need to do research not just at the field scale, monitoring bioreactors, but research with the mechanistic processes of wood chips to design bioreactors better. So I'll just end with, we know that bioreactors work. We've shown that here in Illinois. I'm not super happy with 20%. We need to do better than that, but that's where our research comes in, and that's where NREC can really help. And then my last point that I want to leave you with is specifically for the NREC board. I won't make you raise your hand and embarrass you, but specifically for the NREC board, you know that you do not just fund research. You're funding people, you're funding educational outcomes, you're funding experiences, you're funding friendships. So for that, thank you.